Hi everyone. Today is my third lecture on the mathematics behind the coronavirus or COVID-19. And I had previously two lectures on this, and I tried to explain in a simple way how mathematics can help us to understand of what's going on right now everywhere. So this is a very nice mathematical model called SIR deterministic model, and it uses all kinds of mathematics starting from arithmetic, algebra to differential equations. In the first two lectures I tried to explain this by using arithmetic and algebra to show how these people are getting infected. So just to refresh your memories if you have seen those lectures. As I say, in a community, it could be a country, a city, or a state. Right now, people are divided in three parts or three compartments. One are the susceptibles who can get infected, and the other ones are the infected ones, as we know. And finally, we have the removed ones. The removed ones, people can get infected, then they can be removed. Removed means they can die, which we want to prevent that, or they can recover, which is the best. So now I talked about the flow. I said there's a flow from susceptible to infected and from infected to removed ones. So basically we call those S of t, I of t, and R of t. In mathematics, these are state variables. Why do we call them state variables? Because they change with time. And if we add all these people, we get n, which is the population. And that could be the population, as I told you, of the country, of a city, or the entire world. In this model, we assume that n is constant. It doesn't change. It's not usually the case, but it's still a good model to predict what's going on and what's going to happen in the future. Now, talking about the flows, last time we kind of started that in an easier way, but today I want to use some calculations using calculus and differential equations. So if you have those classes, it's going to be probably easier for you to understand. So now starting with the first flow. This is the instantaneous rate of change, ds over dt equals to negative a times s times I. Where that comes from, let's look at it. The rate of change of the susceptible people instantaneously is proportional to s, number of people, number of susceptible people, and I, number of infected people. Why? Because those two quantities are in touch with each other. I took a simple example. We have two infected peoples and three susceptible people. Let's see how many ways they can get in touch with each other. So it's pretty straightforward. So this person can get that person infected, or that person infected, and so on. So we have 1, 2, 3, 4, 5, 6. So this is the multiplication principle. So 6 ways these people can get in touch with each other. If we have 2,000 here and 3,000 here, then it's going to be 6,000. However, each time these people they get in touch with each other, not necessarily all of them are infected, or not necessarily they get in touch together at that moment. So therefore, we have a constant here, which is the constant of proportionality. That's how we call it. In this case, we call it the infection rate. So that's why we write ds over dt equals to negative a times I times s. So instantaneous rate of change is proportional to I and s. And this is a non-linear system because we're multiplying two state variables together. Negative because number of susceptible people decrease. So that's the first equation. The second equation is di Well, let's go to the third one first, it's easier to understand. These are number of people recovered. Same thing, the rate of change of recovered people is proportional to number of people infected, and there's always a proportionality constant, and that constant in this case is called the recovery rate. Getting here, there is an inflow and outflow, so that's the most important part. So if I write that, so it's positive A times A times I minus BI, so that minus that. What's our goal? To reduce that. So now a calculus question here. First of all, to reduce that, we know we're going to get the peak and then come back. So how do we find the maximum of a function in calculus? So, or if I read that question, when I of t reaches its max. In calculus, we learned if you want to find the maximum of a function, you take the derivative of that function and put it equal to 0. But what is the derivative of that function? We have it here. So it's di dt equals to 0. Well, the derivative is also called I prime of t. Or if I take the right side, I put that equal to 0. If I separate them, so I get a times s times I equals to bi, I can cancel the i's and I'm left with a times s equals to b. If I divide both sides by b, then I get a times s over b equals to 1. But what is this a times s divided by b? We call that R0 or R0. Sure, we have heard that from the news all the time. That's called the basic reproduction number. Now, once this equals to 0 or R0 equals to 0, we're at the peak because the derivative equals to 0. But what can happen? So the second case, if di over dt is positive, then it's a growth, or R0 is greater than 1. If di dt is less than 0, then it's a decay, or R0 is less than 1. So now coming back, we can, to solve these differential equations, again, we have 3 equations. That's why we call this a system of nonlinear equations, of differential equations. Solving it is pretty complicated, but just having the rates, we can kind of make the analysis. Like the first part, I did it here. Having that, we can graph those functions. So what happens, the orange graph here are the susceptible people. We start from a number and they go down because they get infected. Then the infected ones, they go up. And the red one are the recovered ones, then they go up. Again, these two are logistic models. Why? Because the susceptible can, if everybody gets infected, then almost the number of susceptible people are 0. And if everybody gets recovered, then it's going to be, the number of recovered people are going to be the people, the population. So that's not the case all the time. However, so what's going on here? When these two are equal, R and S, they cross each other, I of t reaches its maximum. What's the best way to reach the maximum? This is not a good model, because if I drew this line, this is the healthcare capacity. So if this curve is over that line, that means the hospitals cannot take care of everybody. They get overcrowded. So we're going to have more deceased people. So what we need to do is to flatten the curve. We want to flatten this. So this number, this peak, is less than the healthcare capacity. How do we do that? It's using R, or A times S times B. I want to write that for you again. A times S over B. This is like a fraction. We want to reduce this fraction. There's, well, reduce the susceptible people, we need vaccination, but we do not have that for now. B is having antiviral medicine. It's not available like that. So what's left is A. So we want to bring down A. If we bring down A, then we get a curve like that. How do we bring down A? Is by social distancing, washing hands, staying home. So these are important factors. It's going to make that small, so it's going to flatten the curve. That's why we right now we are ordered to stay home or follow this, and don't forget to do that every day. It's very important. As they say, this is the time. If you become a couch potato, then you can save the world. So thank you for watching. Please stay safe and don't forget to wash hands and social distancing. I'll see you next time.